Research Accelerator, and we bring together the brightest minds from around the world in space science and machine learning and pair them together to tackle problems in heliophysics, astronaut health, lunar exploration, and earth science. This is hosted by the SETI Institute in partnership with NASA, and this is our 5th year that we have been doing this program. And this year we are here virtually from around the world. We have 8 teams this year that are at FDL in the US going through our 8-week program, and we're currently at week 6, where teams are continuing in the improvement phase. And today I have with me the Astronaut Health team. So I'm very excited for all of you guys to have joined us today. No, this is a busy week for you, but this is a really, really exciting challenge. So to kick us off, I'd love to have each of our researchers introduce themselves. So we'll start with Kia.
Thank you, Sarah. Hi, everyone. I'm Kia Cazelli. I obtained my PhD in electrical and computer engineering with concentration in applied probability and statistics from Cornell University. And I will be joining Mayo Clinic as a postdoctoral scholar in fall.
Great. Wonderful to have you, Kia. And Adrian?
Hi, I'm Adrian Horfrost. I'm here in Pennington, New Jersey. I got my PhD in marine sciences at the University of North Carolina at Chapel Hill, and I'm now a postdoc at Rutgers University. I study how microbes impact carbon cycling and how they have co-evolved with the Earth over time to understand the links between biology and planetary systems.
Great, thank you for joining. And we have Sam.
Thanks, Sarah. So yes, I'm Sam Budd from London, UK. Currently halfway through a PhD in medical image computing at Imperial College as part of the Biomedia Research Group.
Great, thank you, Sam. And Arno.
Yeah, thanks, Sarah. I am Arno Blas. I am a PhD student at the University of Oxford, and my work is mostly focused on AI safety and adversarial robustness in machine learning.
Wonderful. Thank you, Arno, and thank you all again for joining. And thank you to our viewers. I know that we have people from around the world, so I see Norway. Welcome. To kick us off, I'd like to start with understanding a little bit more about the awesome challenge that you guys are working on. So Sam, can you explain the challenge for us?
I sure can. So as you can see behind us, our challenge this year for the Astronaut Health team is to study long duration missions and cancer. So the big question we're trying to answer is, can we use causal inference methods to understand the molecular basis of cancer in high radiation environments, such as long duration missions to the Moon and Mars. And this year, our project is partnering with the brilliant Mayo Clinic, who have provided us with the world's largest data set of colorectal cancer data, consisting of 100 cancer tumors samples, for which we have lots of data on each of these, including genetic data, epigenetic data, microbiome data, clinical metadata, and a pseudo time series data. And we say a pseudo time series because it's not a real time series, as when your clinician discovers you might have cancer, they get to work treating it right away. Nobody's leaving any tumors in for you, for scientists to study how they progress, which is one of the big challenges in understanding the causal mechanisms in cancer. So using this data, we want to build a test bed for building these causal inference methods. And if we can understand better how cancer initiates, progresses, and evolves, then we can develop better prevention strategies and better understand the risks of sending astronauts on high-risk missions beyond our planet.
Wonderful. Thank you, Sam. That was a great overview of your challenge. And I'd like to turn it over to Adrian to talk a little bit about why this challenge is so important and why it matters.
Yeah, so there are really 3 big prongs to why this challenge is hopefully going to have a big impact. I mean, of course, we want to understand the causal drivers of cancer so that we can better treat cancer here on Earth. There's billions of dollars that are spent every year on diagnosing and treating cancer patients. I think most of us have, somebody in their life who's been touched by cancer. So we all know how big of a problem it is, and a big challenge. So if we can understand the causal drivers better, we can start to target treatments at a more individualized level and hopefully have better success rates in treating and curing cancer. So that's, our earthbound reason. There's also, of course, the astronaut health angle to this as well. So we are working towards sending astronauts on long duration missions. A mission to Mars is going to be a minimum of 2 years in just transit time, and then of course the time that they actually spend on Mars. So they're going to spend a lot of time out in these very harsh conditions and be exposed to really high levels of radiation, which of course is a risk factor for causing cancer. So we need to, it's our imperative to sort of safeguard their health by having better approaches to assess the risk of astronauts at an individual level. So by understanding the causal drivers, we can start to do that individualized risk assessment and understand, can we send this person to space for years at a time in the first place? And can we help safeguard their health while they're in space? And of course, safeguard their health once they return as well. And finally, so I come from a biological background, but not a cancer biology background. So I think one of the really exciting applications of this is just the causal inference framework that we're developing and the applications that we could have in all biological systems. So if you study biology, it's a very, very common problem. Sam talked about some of the data we have. You have this huge high dimensional data set. The interactions of all of these different data types between each other is very complex, but it also tends to be very expensive and time consuming to gather that data. So you have a very high dimensional problem, low sample size, and when you're just looking at correlations, it's very hard to understand the mechanisms of the system and actually model biological systems really well. So hopefully the sort of modular causal inference framework that we're developing will be broadly applicable to biological systems in general.
Great. Thank you, Adrian. And I love that your challenge in particular is so great because it focuses both on the impact on here on Earth with us, as well as the impact for long-term duration space missions. So it's really, really great work that you guys are doing. Kia, I'd really like to turn it over to you to talk a little bit about some of the approaches that you are taking and the tools that you guys are using.
Thank you, Sarah. So part of the challenge is to process the data that we have gotten from Mayo Clinic. That data is multi-omic. It has different features. It has different raw data that we have to process before being able to apply any sort of machine learning methods or algorithm on it. So we have spent significant time on utilizing the biological understandings that we have from these mechanisms into having a more refined data set that can be used in our machine learning framework. And for the machine learning part, we have built an ensemble of different machine learning frameworks that are state-of-the-art for causal inference. And the reason that we have decided to move toward an ensemble approach as opposed to just picking one is that each of these state-of-the-art methods, they have an operating assumption which is required for guaranteeing a satisfactory performance of the methods. We know that biological mechanisms are complex, and oftentimes they do not satisfy these restrictive assumptions. So it's really helpful to have different methods that we can compare and analyze to have a more concrete outcome of the method.
Great. Thank you, Kia. And I'd also like to thank our viewers that are joining in Kenya, Germany, San Francisco, Ontario, Spain, Ghana. Thank you guys for joining. And I have a couple more questions for the team, but I wanted to invite the audience. If you have questions, please share those with us, and we're going to go into the Q&A here shortly. But you guys are in week 6. You're most of the way through the program. I'd really love to hear some of the roadblocks that you guys are experiencing and how you guys are working on tackling that. So for that, I'll turn it over to Arno.
Yes, sure. So working with cancer data, yeah, is quite challenging, and that there are definitely a couple of reasons why. I'd just like to highlight 3 of them right now. And to begin with is something that Sam already mentioned concerning the amount of data we have. So as he told us, we have data from around 100 patients at Mayo Clinic from their tumor samples. And that basically constitutes the largest multi-omic colorectal cancer data set in the world, which for most causal and statistical methods, the ones that we're using, is still considered extremely low, low number. And that makes it hard to fit good models to the data and to come to reliable conclusions without very strong prior assumptions. So that's a big challenge here, and that gets kind of aggravated by the second, which is that the data is inherently very high dimensional. So we have a lot of features. We have, as Sam said, a combination of genomic, of epigenomic, of microbiome data for each of the tumor samples. And each of those samples then has thousands of features. So a single feature, for example, being the occurrence of a genetic mutation at a particular position of the DNA, or for example, the amount of a certain type of bacteria being present in around the tumor. And for all the kind of statistical and causal models that we employ, working with such a high number of features or dimensions is both statistically but also computationally difficult. And we're very fortunate to have partners such as Google Cloud that provide us with a lot of computational power. But still, of course, the statistical and causal inference remains hard, especially in combination with a low sample size. So if you only see a few examples, it's very hard to understand the distribution behind such a high dimensional feature set. And yeah, the last and also very challenging kind of pitfall or roadblock that we face and that we're currently trying to circumvent is that, well, all of us, at least those from the machine learning side with a background in machine learning and not so much in biology, were quite surprised about the lack of ground truth, if you want, so about the lack of definite understanding of causal relationships in colorectal cancer research so far. For example, it is known that some bacteria often happen to be present when the colorectal cancer is present, and vice versa, but it's not really clear which one causes which way around is the causal relationship here. And in general, there's basically no causal relationships known for certain in colorectal cancer research. And that makes it difficult for us to verify and to validate our model and our framework, and to check that things and causal relationships we discover are actually valid. And so we try to circumvent this by cross-validating our framework on synthetic data, so data that we create ourselves that has some modeled inherent causal relationships, and then see if the framework we use, if the methods we use can recover these, because obviously if they couldn't, then we wouldn't expect them to be able to do that on the real data we have. And also, as a side effect of this, it's also hard to decide where to look. So which feature do we want to try and understand and explain by which cause? Because there's so many features, there's almost endless possibilities to do that. And there's little intuition and guidance from existing research as to where to look exactly. And in order to tackle that, we build our framework as flexible and modular essentially as possible, in order to apply it to as many potential causes and effects as possible in a fairly explorative way. And as Adrienne mentioned, also with a thought behind of potentially using it for even different biological mechanisms beyond cancer at one point in the future.
Great. Thank you, Arno. And it sounds like you guys have a lot of hard problems that you guys are tackling. And I'm really excited in the coming weeks to see everything that you guys accomplish. So I'm going to go ahead and ask each of you to share what is your desired outcome for this challenge. And to kick us off, I'd like to have Sam go.
Oh, well, we're going to win a Nobel Prize, obviously.
Great.
That's the big goal. No, but we just want to be able to contribute and develop something that can be used by people beyond us and our team, and hopefully draw out some interesting insights that can go on to be explored further and be of use to SETI and NASA and all of our brilliant partners over the next few months.
Great. Thank you, Sam. I have every bit of confidence that you guys will accomplish that. So Arno.
Yeah, so me personally, I'd say since I'm working on a work stream inside our project that concerns these relationships between the microbiomes, between the bacteria and the cancer, and understanding, what happens there essentially. I think it would be really great if by the end of this we could get some more understanding of the causal direction between mutations and between cancer and the microbiome present.
Thanks, Arno. And Adrian?
Yeah, I'll echo what Arno said. I think one thing that we can possibly do that'll be really useful to people working in the lab or clinicians is identifying some of these potential causal drivers, and not just the causal drivers, but the potential directionality, because that could really help understanding if it's, is this microbe driving some methylation pattern that we see, or vice versa. That'll give some strong indications to scientists to, okay, how can I design an experiment to test this that will most likely be able to describe that mechanism. And I'm also just really excited about the potential applications outside of biology in high dimensional systems with low sample size, trying to look at links between biology and the Earth, for example.
Awesome. Thanks, Adrian. That's exciting. And Kia.
I'm building up on what Sam, Adrian, and Arno said. So we are really trying to have a flexible framework that is that could be useful for different stakeholders, such as NASA or Mayo Clinic. So from NASA's perspective, the risk assessment and evaluating uncertainty for astronaut health, that's a direction that is useful for Mayo Clinic. For example, clinicians and biologists could test their hypothesis. For example, that example that Arno gave about the microbiome relationship with colorectal cancer, these are the sort of hypotheses that are really interesting to see the outcome of, like to see what direction is. So I think like keeping the framework flexible is what is the most interesting part of the outcomes.
Great. Thank you, Kia, and thank you, team. So again, thank you for joining us in the audience. If you do have questions, please start sending us those in the while we're waiting for some questions to come in. I would like to turn it over to our CEO of the SETI Institute, Bill Diamond, because I believe you have some comments on both this challenge and FDL in general.
Sure. Thanks, Sarah. And thank you, team, Kia and Adrian and Arno and Sam. It's great to have you here. And I, first of all, want to thank you for taking time out of your incredibly intense schedule here, where you're trying to win a Nobel Prize in 8 weeks. Really appreciate your sharing this particular challenge with the audience. And I'd like to thank the audience as well for joining us. As Sarah's already mentioned, we've got people from all over the world tuning in today. So we've got people from India and Holland and Germany and Spain, Brazil, Japan, Ghana, Canada, lots, of course, from all over the US. So it's terrific to have everybody joining us today and to see how, again, it's a global village which comes to learn about the things we do here at the SETI Institute and about the FDL program. It's also wonderful this year to have a challenge in the FDL program that is supported by a new partnership with the Mayo Clinic. It's really fantastic. Mayo got involved with us last year in supporting an astronaut health project looking at cardiovascular health in astronauts and again, early detection of health issues that might impact long-term missions. But this is really exciting to have Mayo completely supporting a team this year, providing data, providing funding, technology, and mentorship and subject matter experts. So we're very excited and honored to have Mayo with us this year. And this is an amazing challenge, really terrific to see. And, you know, Sam pointed out a goal which is both aspirational and specific, the Nobel Prize, why not? But this work really is important though. And it does what I, you know, Sarah mentioned, the relevance of this particular research project, not only to NASA and human interest in, you know, exploring the cosmos, even neighboring visitations such as Mars or other places pose incredible challenges to human health. And if we can take and learn from efforts to understand issues like causal inference in cancer that could impact things like astronaut selection or the health and safety of astronauts and missions, that at the same time has immediate and direct benefit to humanity in general here on Earth. I mean, that's doubly impactful. So it's great and very exciting what you're doing. The other thing I wanted to say for the audience was that, you know, some of you may be familiar with our FDL program, some of you may not be, but this is the 5th year of the program. And we've had teams like this, like the one before you, doing all kinds of research on earth science, heliophysics, astrobiology, planetary defense, all kinds of different challenges. And, but each year up until now, the teams have had the advantage of being able to physically be together and work together. This year, for the first time, the FDL program, like so many things around the world, is being done virtually. But we're demonstrating the ability of teams to collaborate and perform world-class research in a virtual environment. And I think that's extraordinary. It adds an additional dimension of difficulty to the challenge that all these teams are working on. But it also demonstrates, I think, something that goes far beyond FDL itself, and that is, can interdisciplinary teams work in a virtual environment collaboratively through platforms such as Zoom and others, and still achieve extraordinary results? And I think we're seeing that we can do that this year. So we have scientific experiments and we have social experiments going on simultaneously, and that makes it doubly exciting this year, but doubly challenging. So hats off to the team for all your extraordinary work and the challenges you're working around and overcoming in order to get these great results. So once again, thank you so much. And I do hope that you know, you achieve all the goals you're looking for and outcomes you're looking for. I think this could be the beginning of a series of challenges that grow and expand from this initial foray in terms of things like causal inference in cancer, but could take beyond. As Adrian pointed out, there may be lots of ways that this morphs into other research areas. So this is the beginning of something I think very exciting. We're delighted to have you with us, and thank you so much for your work and your efforts, and again for sharing your time with our audience today.
Great, thank you, Bill. And thank you to the team for joining us on this social experiment. So we have a couple of questions from the audience. So the first question is, we know that there are a lot of health risks for our astronauts that go into space. Do we know what is the maximum time for an astronaut to stay off the Earth without compromising their health? And so Adrian, I'll turn it over to you.
Yeah, so I think the sort of unsatisfactory but more accurate answer is it really depends on the astronaut. So one of the things that is potentially impactful and important about understanding causal drivers of cancer is that you can then start to think about, okay, given this person and their genome and the things that I know about their personal history, can I assess their individual risk for when we send them out into space, how sensitive they're going to be to the higher radiation conditions or something like this. Right now, my understanding of how NASA assesses this is basically on the population level. You look at, you know, if we average over all people, what's the occurrence of of cancer in this population set. And so that's how you assess risk. But of course, it's very variable over individuals. And there may be a much more precise answer that you could give for an individual. So I think hopefully the goal of this project, and I know the NASA Astronaut Health larger team that's part of NASA is definitely trying to think along those lines, so that we can give a more specific answer to the what's the maximum time that we could expose this person to space conditions.
Great. Thank you, Adrian. I think that that's a great answer on personalized health. So the next question that I have for all of you is, would you go on a long-term duration space mission? Adrian, since you're still up, do you want to go first?
Yeah, I don't know. You'd have to convince me it's safe. So,
well, hopefully with what you guys are working on, then it will be safe, or we'll be able to assess the risk. So I'm with you. I'm perfectly fine hanging out here in mission control. Arno, how about you?
Yeah, I mean, it would be quite a challenge, wouldn't it? But I have to say that I'd probably just miss my life on Earth too much to go on such a journey, to venture on such a journey. But yeah, it's definitely tempting. But honestly, probably the answer would be no, if I'm honest.
All right. I'm curious now. Would you go on a short-term duration space mission? Or no?
100%.
Okay, cool. Awesome. How about you, Kia?
Yeah, absolutely. I have trust in science, and I think that's a big step for humankind and myself. So yeah.
Awesome. All right. Kia signed up. How about you, Sam?
Yeah, give us a few more months working on this project, and I feel a lot more confident going up there. And as long as I've got an awesome mission patch on my shoulder, I'm raring to go.
Great. And this team has been really, really wonderful with their creative work for the presentation. So I can only imagine what mission patch you all would design for your mission. And I think that we're kind of getting to the end here. Bill, do you have any final comments? Would you go on a long-term duration space mission?
Yeah, so I guess it depends on how we define long-term. Like, would I go to Mars and be there for 6 months or even a year and then come back? You bet. 5 years? Yeah. So like Arno said, I might miss Earth a little bit too much. I think Elton John said it well when he said, Mars is not a great place to raise your kids. A beautiful and extraordinary experience, but I'd want to come back, that's for sure. In any case, again, just a big thank you to the team. Congratulations on the progress so far. I know you've got still a lot of work yet to do, but I have every confidence that you're going to achieve the objectives that you've set out to do. And I think we're going to learn a lot from your work. And as Sam said, we'll be more comfortable putting on the spacesuit and heading off into a long duration mission if you guys are successful. And we learn a lot, so I think we will. So thanks again. It's great to have you with us. And Sarah, of course, thank you as well for quarterbacking the call and for handling all these calls and really leading the FDL effort as you do year in and year out and do an extraordinary job. So it's great. And thanks to our team in the background that's made this morning's presentation possible. And last but certainly not least, thanks to our audience for tuning in and listening to what this extraordinary team of researchers is doing in the FDL program this year. So with that, from Mountain View, California, where the SETI Institute's lights are off, but the work goes on, thank you and good day, everybody.